Alright, here is your note. You will notice at the top of your page there is a website. If you could, I will put it on the website so that you could just click on the link, but if that's not available to you, see if you can find it. And it's just kind of a simulator to help you understand the VSPER theory. So let's take a look at the note for this. VSPER is just another model. It's a name for a way in which we can place atoms around a central atom and kind of visualize what the structure will actually look like. So now we're going to talk about the geometry, the angles of the bonds, because all of those play a role in the shape of the molecule. So that's what we're really interested in now. And VSPER is pronounced VSPER with an E between the V and the S. However, there is no actual E there. And it stands for valence shell electron pair repulsion. A really fancy way of saying, yes, electrons do not like each other. They do not want to be close to each other. They repel, a pair of electrons will repel another pair of electrons in a bond. So they want to be as far away as possible, the lowest energy that they can be in. So the closer the bonds are to each other, you see that increase in energy. So first thing we need to assume is atoms in a molecule are bound together by electron pairs, and these are bonding pairs, and the other one is lone pairs of electrons. So you can have two atoms together with multiple bonding, and sometimes when you draw your Lewis structure, you have a lone pair that surrounds that central atom, and they have a huge effect in the shape of the molecule. Other things we can assume is the bonding pairs and lone pairs want to adopt positions where their interactions are minimized. Okay, so some electrons really want to be as far away from each other as possible. So lone pairs occupy more space than bonding electron pairs. Just like I said yesterday in class, rambunctious teenagers who want to have the rule of the roost. So let's take a look at some of the shapes that we can get. Now, we did not have time to do this balloon thing. We're a little bit behind, so I'm not going to do it, but if you really want to do it, you can come in at lunch and play around with balloons. However, I think the concepts, you guys are old enough to kind of figure out what's going on. When you have two atoms bonded together, so we're not talking about orbitals here. I know that balloons kind of look like the p orbital, but we're not talking about that. We're talking about the actual shape of the bond. So you have a central atom, and you have two branches. Okay, so this is kind of representative of a branch. So a central atom and two molecules on the side. This is kind of the shape that it gets, 180 degrees. We call that linear. When you have three branches, these electron pairs, like a balloon, will push each other away in a 120-degree angle. So you can see that. Right, you have this 120-degree angle between these two. Okay, and same here. This is a 120 degrees. So we're going to take a look at some examples. Oh, that's really bad. Sorry about that. So let's take a look at some more branches. So this is actually called trigonal. All right. Next one, when you have four branches, 1, 2, going into the page, out of the page, and on the same plane as the page, you have this 109.5 degree angle. Here you can see balloons Doing the same thing if you have 4 balloons together, this is typically the shape that you would get. And we call that tetrahedral. Next is 5 branches, and we call this trigonal bipyramidal. Think to yourself for a minute, why is it called trigonal? Where do you see that triangle? And how is it bipyramidal? So let's just take a look for a second. Trigonal because you have this triangle right here. Okay, so if you look at the balloons, there's your triangle. Okay, and pyramidal because there is this pyramid structure that forms right on top of this, and a second one, then bipyramidal. 2 different angles here. So if we look at the bond angle between these two, you get 180 degrees, or here. So therefore this is 90 degrees, right? And then between these 3, you get 120, and 120. So 90, 90, 90, and 120. Okay, so that is 5 branches, and the name for it is trigonal bipyramidal. Octahedral. Octa normally refers to 8. So let's take a look. Where does 8 come from? So octahedral comes from this shape. So you have kind of like a square right in here, 4, and you have a like kind of a pyramidal square opposite of that. That's why it's called octahedral. Okay, so a square, basically 2 pyramids with a square base on top of each other. So 4 plus 4 is 8, octahedral. The bond angles here for all of them. So for the 5, it was 2 different type of bond angles. You got 120 degrees and you got 90 degrees. So here you have 90 degrees, 90 degrees, 90 degrees, 90 degrees, 90 degrees. Okay, and that's called octahedral. So if you had 6 balloons together, this is the kind of shape that you would get. And it's called octahedral. So how do we predict geometry? First thing you're going to do is draw the Lewis structure. Focus on the central atom. Look at how many branches it have. A lone pair is going to count as 1 branch. A double or a triple bond also only counts as 1 branch. So here, easy mistake to make. So make sure that you understand that. This part right here, okay, that a double or a triple bond count as 1 branch. Because a double bond is not going to influence the shape of the molecule. The other one that you need to remember is nitrogen, because nitrogen, if you draw it, you'll remember that it's N 2 dots. 1, it's 5, so 1, 2, 3, 4, 5. Sometimes we forget that nitrogen has this lone pair right there. Okay, so make sure that you have, you make a note of that. And that also, even though it's a lone pair, it's going to count as a branch. And then you're going to look at the coordination geometry. And what I mean by that is you are going to look at this. So is it linear, is it diagonal planar, is it tetrahedral, is it trigonal bipyramidal, or octahedral? Now, you'll notice you're going to get this in a test. Not positive if you get the names of them, but you will get the shape. Okay, so you'll have to remember these names that go with it. But when it has no lone pairs, it's 3 atoms, 2 bonds, you're going to get a linear molecule, and that's it. However, trigonal planar, if you replace one of the bonds with an electron, that electron is going to place more, is going to need more space. Again, rambunctious teenagers are going to need more space. So this bond angle is going to be a tiny bit smaller than 120 degrees. And now we're going to call that bent or angular. Then, when it gets to tetrahedral, you have a couple of options. You could have 3 bonds, 1 lone pair, or you can have 2 bonds and 2 lone pairs. So few things can happen. You can have tetrahedral like normal, 109 degrees, 0.5, or you can have this lone pair. Again, that lone pair is going to force extra repulsion on these bonds, forcing them down, so you're going to have less than 109 degrees. Same with this guy. Okay, and now you have a trigonal pyramidal shape, because there's your triangle. Okay, and it forms kind of like a pyramid, right, with that central atom. Here you get a bent or angular shape. So this one is an example of water or sulfur dioxide. 5 trigonal bipyramidal. You can have 1 lone pair and 4 bonds, 2 lone pairs or 3 bonds, and you can have this linear shape with 3 lone pairs around it. Okay, so here you have a seesaw. I like it as a seesaw because you have this lone pair. And watch out, nitrogen normally forms this because it has that lone pair, so don't forget that. And then you get this T shape, okay, and then you can also get this linear shape. And here are more. So octahedral has plenty more. So again, you can have a T shape, or in a T shape, octahedral T shape, or you can have a linear shape, or you can have a square planar. So here you have, again, that 90-degree angle, and then here you have your 90-degree angle. And same with this is a square pyramidal, okay, and your regular octahedral. All right, so you have this handout, or you will get it. It's also in your textbook at the back, but don't worry about copying it because you're going to have it in your notes, and you will have a copy of this during your test or final exam. So let's take a look at water as an example, H2O. You're going to draw the Lewis dot diagram. Central atom is oxygen, place it with hydrogen. So how many electrons do I have? I have a total of 8. So 2 electrons between the bonds. Then I fill up to follow the octet rule. I'm happy. The structural diagram is now going to look like this. And so how many groups are on the central atom? 4. So how many bonds? 2 bonds, 2 lone pairs. So the name of this would be a bent shape. All right. Now this one's a little bit more tricky. I do want you to pause the video, and I want you to do it and then see if you came up with the correct shape. So I'm gonna just pause it. You pause it, and I'm gonna go back to this screen, and I want you to figure out if you got the right one. Okay, so choose